right, so yesterday we did some with L'Hopital's rule. As I recall, yesterday we handled the 0 over 0 case, and we handled the infinity over infinity case, and I think we did the infinity minus infinity. So I think we did those three setups. So there's three more that we need to talk about. The other three possibilities for indeterminate forms are 0 times infinity, or infinity times 0, 0 to 0, and 1 to the infinity. So those are the other three indeterminate forms. All right, so let's grab one out of the book here. How about the limit? As x goes to 0 from the right of x cubed cotangent x. Well, when x approaches 0 from the right, x cubed gets close to 0, and cotangent gets close to remember, cotangent is cosine over sine. So can you plug 0 into cosine over sine?
0.
Cotangent of 0 is 0? Or tangent of 0 is 0? Remember that cotangent is cosine over sine. So I can't plug 0 into that, can I? So that's where one of the asymptotes happens, isn't it? So if one of the asymptotes is happening, then this is getting close to infinity. Okay. So this is in the form 0 times infinity. So if you have something in the form 0 times infinity, what you want to do is you want to take one of these two and drop it to the bottom. And that'll make it in the form 0 over 0 or infinity over infinity. No. Infinity times 0 is... Because remember, this is not exactly 0. This is really, really close to 0. Not yet. Remember, we can only use L'Hopital's rule if we have 0 over 0 or infinity over infinity.
So is it just infinity over infinity, or is it negative infinity?
Yeah, the infinities can be positives or negatives. Those don't matter. It can't be 0 over infinity. But 0 over infinity is easy. 0 over infinity is 0. If the top's getting really small and the bottom's getting really big, a really, really little number divided by a really, really big number is really, really close to 0. So 0 over infinity is not a problem. All right, so anyway, like I say, we need to make a decision. We're either going to move the x cubed to the bottom or move the cotangent to the bottom. So what we're going to do in this case, I think it's easier to move the cotangent. So we're going to move this as x cubed over... When I move a cotangent to the bottom, it becomes a tangent, doesn't it? Now if I try to plug 0 in, I'm in the form 0 over 0. Can I now use L'Hopital's rule? Yes, I can. So that's the limit, as x goes to 0 from the right, of 3x squared divided by, what's the derivative of tangent? Secant squared. Can I now plug 0 into that limit? Well, when I plug 0 in, I get 0 on top. What do I get on bottom? Secant of 0 is? So 0 over 1, which is 0. That's correct. Why wouldn't I use the quotient rule there? Why? Because remember, L'Hopital's rule, I agree we have a fraction here. And anytime you see a fraction, it's tempting to use the quotient rule. But L'Hopital's rule says don't use the quotient rule. L'Hopital's rule says do the really easy thing. Just take the derivative of the top and then take the derivative of the bottom.
It's like two different functions.
Correct. You treat them as two separate functions. You treat them like this bar doesn't mean division anymore. Just do the derivative of the top, derivative of the bottom. So we're definitely not doing the quotient rule. Definitely not. All right, but anyway, there's your technique. Anytime you have infinity times 0, you're going to take one of the two things and you're going to move it. Let's see if I can find another one that looks like that. The answer in this case is 0, correct. Oh, I can't find one, so I'll make one up. How about the limit as x goes to 0 from the right of x ln x? Limit as x goes to 0 from the right, correct. Well, again, what's happening when x gets close to 0? When x gets close to 0, x gets close to 0. That was a tough one. And when x gets close to 0, ln x gets close to, not 1. ln of 1 happens to be 0.
You pass that, you're approaching 0.
Approaching 0. Natural log of 0 is undefined. That's true. So what's happening when I get really close to 0? That's where the asymptote is. That's right. And if you look at the ln graph looks like this. So when x gets close to 0, my ln is getting close to negative infinity. So this is in the form 0 times infinity. In this case, it's negative infinity. We don't care about minus signs. All right, so what do I do? Move what to the bottom? Which one? ln x. All right, if I'm going to move ln x to the bottom, that's going to be x. And then I'm going to have to write this as ln x to the negative 1. No.
That's if it's on the x.
ln x to the negative 1 is not the same as ln x to the negative 1. It would have been nice if we could have taken the derivative first. I agree. But we couldn't. We got to move it down. So now we're in the form when x gets close to 0, this one gets close to 0. And when x gets close to 0, what's ln x to the negative 1 get close to? Well, ln x itself gets close to negative infinity. What's negative infinity raised to the negative 1? It would be 1 over negative infinity, so that would be 0. So this is now in the form 0 over 0. So now we can use L'Hopital's rule. That's the limit as x goes to 0 from the right of, what's the derivative of x? I'm going to say 1. What's the derivative of ln x to the negative 1?
It's negative 1 ln x multiplied by 1 over ln x. No, sorry, 1 over x.
I got to use the chain rule, don't I? I bring the negative 1 down. I subtract 1 from my power, so that's going to be negative 1 ln x to the negative 2. But then I got to take the derivative of the inside. The derivative of ln x is 1 over x. Now I'm going to simplify that. That's the limit as x goes to 0 from the right of negative x ln x squared. Correct? Because the negative 2 power here on the bottom, a negative 2 power on the bottom tells you to move something to the top. And then a 1 over x, I flip and multiply, I get an x, and there's my minus sign. Now what? Is what? It looks like almost where we started, except now it's even worse, isn't it? We started with an ln x, now we have x ln x squared. We made powers get bigger. We made it worse. Shame on us. Oh no. So what do we do? We did what? We made a bad choice. We moved the ln x to the bottom. We probably shouldn't have done that. We probably should have moved the x to the bottom. So what do? We say, oh crap, and we start over. It's kind of like when we first started doing integration by parts. Sometimes we made a bad choice for u, didn't we? And we saw that when we did, we started over. All right, so I think, let's try again. Limit as x goes to 0 from the right of x ln x. That's going to be the limit as x goes to 0 from the right of ln x over x to the negative 1. So let's try moving the x to the bottom this time. Now we would be in the form infinity over infinity. So we can use L'Hopital's rule. That's going to be the limit as x goes to 0 from the right. What's the derivative of ln x? 1 over x. What's the derivative of x to the negative 1? Negative x to the negative 2. So that's the limit as x goes to 0 from the right of 1 over x times x squared over 1 with a minus sign. So the answer is negative x, but then x gets close to 0. 0. Questions on that?
Yeah, when would we have one that's 0 times infinity and it would be 0?
I knew somebody was going to ask that question.
What's the point? How is that?
I knew somebody was going to ask that question, and I didn't know if I was going to have an answer. His question is, so far we've done 2 examples where we have 0 times infinity, and both times we've gotten 0. And I told you that 0 times infinity is not always 0. So he wants an example where 0 times infinity does not give him 0.
What part of the indeterminate definition makes 0 times infinity not, or what makes it?
Well, what makes it indeterminate is it depends on, in a sense, which one's going faster. What we've seen so far is in both of these examples, x is going to 0 faster than ln x is going to infinity. So this number is getting really small compared to that number getting really big. So this is maybe like 1 over a million when this is 1 over 1,000. I'm sorry, this is 1 over a million when this one's 1,000. And this is 1 over 10 billion when that one's a million. And so this one's getting smaller so much faster that you get 0. I'm looking to see if they have any examples in the book where that happens. And I don't happen to see one. So I guess that's a challenge to the teacher. Find an example where you're in the form 0 times infinity and you don't get 0. I don't have one right off the top of my head. I could try doing some more of these problems in the book and see if they work out that way. But I don't know if it's going to happen or not. They do have the answers for the odd problems. Let's look at the odd problem, see if 45 turns out that way. All right, according to the back of the book, problem 45, the answer turns out to be 1. So let's do that problem. 45, we have the limit as x goes to infinity. Sine of 1 over x times x. According to the back of the book, the answer to this one is 1. X goes to infinity, correct. So when x goes to infinity, x gets close to infinity. And when x gets close to infinity, sine of 1 over x gets close to 0, because 1 over x gets close to 0, and sine of 0 is 0. All right, so this is in the form infinity times 0. Which one do you want to move? X? Okay. So that becomes limit as x goes to infinity. Sine of 1 over x to the negative 1. That's the limit as x goes to infinity. What's the derivative of sine of 1 over x? think of 1 over x as x to the negative 1. You bring the negative 1 down and you subtract 1 from your power. And then what's the derivative of x to the negative 1? Negative 1x to the negative 2. Those reduce out very nicely. Now when x goes to infinity, cosine of 1 over x goes to cosine of 0. Cosine of 0 happens to be 1.
So that sine of 1 over x, that's getting closer to 0 as well, right?
The sine of 1 over x, that was getting close to 0, correct.
All right.
Because 1 over x gets close to 0, sine of 0 is 0.
Yeah.
But the cosine of 1 over x gets close to 1.
Yeah.
Because the cosine of 0, correct. All right, so there, I found an example. Glad I came up with one. All right, so let's look at the other possibilities. And these two work the same way. Once you know how to do one, you know how to do the other. The limit. As x goes to infinity of 1 plus 1 over x to the x. When x gets close to infinity, when x gets really, really big, what happens to 1 plus 1 over x? It gets really close to 1, and when x gets really big, x gets really big.
And so you just get 1.
So it looks like we're getting something close to 1 to the infinity. And that's an indeterminate form. That can be anything. Because remember, keep in mind, this is not exactly the number 1, is it? I'm not saying take exactly the number 1 and raise it to the infinity. 1 to any power would be 1. This is something really, really close to 1 being raised to a really, really big number, though. So even if you take like 1.0000001 and raise it to the 1,000, you're not going to get 1. Let's try that just for fun. Where's my calculator? What's that? There's my calculator. Did I bring a calculator today? Here we go.
Taking like a really small number to a really big number.
No, like 1.000.
So let's say I take a...
0 is 1. Raised to the no prod. That's the guy.
So that one, well, that's not maybe a good example because I had more zeros on my decimal than I did my powers. But you can see the number got bigger, though, didn't it? Even there, raising it to the 1,000 power, the number got bigger because you can see the 1 turned up earlier in the decimal point. So if I take a number that's close to 1, even though it's really pretty small, and raise it to a big power, I might not get 1. Let's try that same one again with a bigger power. How many zeros did I have there? 1, 2, 3, 4, 5, 6. And then raise it to the million. So you can see that's not getting close to 1. That's already 1.1. I mean, it's still fairly close to 1, but it's definitely not like 1.00000. Anyway, so 1 to the infinity in that form is not necessarily the number 1. So here's what you're going to do on these. You're going to call this thing y. We don't know what the answer is, so we call it y. Why y? Because we already used x. And then what? Any clever ideas? Take the ln. That's a really clever idea. Why do you take the ln? Because it will bring the x down. That's exactly right. Ln y equals limit as x goes to infinity of x ln 1 plus 1 over x. Now, what form is this in? When x gets close to infinity, this x right here is getting close to infinity. And when x gets close to infinity, what's happening to this ln thing? Because it's getting close to ln of 1, which is 0. So we're in the form infinity times 0. So we need to move one of them. Do you want to move the x or move the ln? Move the x. It's a lot easier to move the x, right? We just write x to the negative 1 on bottom. So this is the limit as x goes to infinity of ln of 1 plus 1 over x to the negative 1. Now we're in the form 0 over 0. Now we can use L'Hopital's rule. This is the limit as x goes to infinity of, what's the derivative of ln of 1 plus 1 over x? 1 over 1 plus 1 over x times negative 1 x to the negative 2. Got to use the chain rule there. And on bottom I get negative 1 x to the negative 2. Those reduce out. When x gets close to infinity now, my answer is 1. But that's not my final answer. Why is that not my final answer? Because I did the ln. So this is ln of my final answer. So how do I get rid of ln and get my final answer? No. What gets rid of ln? E. So remember right now I have ln of y equals 1. So y equals e to the 1. So there's an example of a limit in the form 1 to the infinity where the answer is not 1, the answer is e. The limit as x goes to infinity of 1 plus 1 over x to the x is e. Questions on that?
Maybe I'm just not remembering. It seems kind of weird you can take ln of y and then make it ln of that without saying it's ln of the whole system of the limit on the inside.
Yeah, I thought I should take that out the limit.
Yeah.
Ah,
That's what, maybe I'm just forgetting some basic thing about limits.
you're forgetting something about limits. The thing about limits is if f of x is continuous, then the limit as x goes to infinity of some function, g of x, perhaps, and you do f on the outside, which is basically what we did. We did ln on the outside. As long as your function is continuous, you can bring that function to the inside of the limit.
Right. Okay.
We don't do that very often. That's probably why you've forgotten it. It's very rare that we apply a function to the outside of a limit. But you can, and the function simply goes inside. As long as your function is continuous. All right, so that's the trick when you have, well, that's not the trick, that's the technique. When you have a limit that's in the form 1 to the infinity, you're going to call it y, and you can do logs on both sides. You're going to do the exact same thing if you have a limit that's the form 0 to the 0. Exact same technique. You're going to call it y, do ln's on both sides. Let's see if I can find one of those. How about the limit as x goes to 0 from the right of x raised to the x over 2. Again, if I try to plug 0 in, I have the form 0 to the 0. And so the technique is call that thing y. And then do ln on both sides. And the whole reason for doing the ln is it allows us to bring that x over 2 down front. Now, what form am I in? When x gets close to 0, x plus 2 gets close to, x over 2 gets close to 0. When x gets close to 0, ln x gets close to negative infinity. So we're in the form 0 times negative infinity. We need to move one of them. Which one's easier to move? the x. And I can just leave that over 2, can't I? Can I write this as limit as x goes to 0? I'm just going to leave a 1/2 right there. And then I'm going to put ln x over x to the negative 1. I don't need to move to 2. The 2 is just a number. All right, now I go to see L'Hopital. He tells me that this is 1/2 times 1 over x, negative 1, x to the negative 2. That's the limit as x goes to 0 of 1/2 times 1 over x times x squared over negative 1. If I think of minus 1 x to the negative 2 as minus 1 over x squared, I flip and multiply. One half x, and when x is close to 0, 1/2 x gets close to 0. But once again, that's not my final answer. Why is that not my final answer? That's the ln of the final answer. ln of y equals 0, which means y is 1. So my final answer, this limit is 1. Questions on that?
So that when you're getting, it'd be negative x over 2, right? And that's getting close to 0.
That's correct. You would have negative x over 2, but as x gets close to 0, negative x over 2 gets close to 0. Correct.
So when we started this problem, we said that limit of x is approach 0 to the positive side of x to the x over 2 equals 0 to the 0.
Well, we said it's in the form
Oh, okay.
0 to the 0.
Okay, so,
0 to the 0 itself is undefined.
okay. So we identified the form. So all along, like I keep writing these equal signs of like 0 times infinity, but it's just in the form.
It's in the form 0 times infinity, technically,
And then we
right?
go through these forms to come up with a solution.
Correct. Correct. Other questions?
Out of curiosity, because like,
Never
the
mind.
situation I was thinking of wouldn't be as interesting. So
It
like,
wouldn't be as interesting.
I was trying to get one where you had like x plus something, so they wouldn't just reduce.
Okay.
But in that case, I don't think you would need to use this form.
Right, you probably then would not be in the form 0 to the 0.
Yeah.
Not unless you rigged it very carefully. I mean, you could make it happen, but it wouldn't be easy, I don't think.
Backwards.
All right, so that takes us to section 8.8. Section 8.8 is about improper integrals. Integrals can be improper in a couple different ways. For example, we've done integrals like this all along. The integral from, maybe we had 1 to 5 of 1 over x dx. That would be called a proper integral. Can you evaluate it? Yes, that's ln x. And then you plug in your numbers, and you end up with ln 5 minus ln 1, which is ln 5. Proper integral, you get a proper number. If I write this integral, however, that's now an improper integral. What makes that integral improper? I've got an infinity on top. That makes it improper. This integral is also improper. The integral from 0 to 5 of 1 over x is improper. What's wrong with that one? 0 is not within the domain of that function, is it? So I can't, that one's improper. That one's also improper. The integral from -5 to 5 of 1 over x dx. What's wrong with that one? 0's in the middle. That's right. So that one's a tricky one. That one's an easy one to miss, that this is an improper integral. 0 falls in between -5 and 5.
And we define natural log to be greater than 0.
Well, remember, technically when I do this integral, I should have absolute values there,
Oh, yeah.
which allows me to plug negative numbers in when I have an integral. I didn't put the absolute values there because I didn't need them because I was only using positive numbers. All right, so that's really the three things, well, the four things. I could have a negative infinity on bottom. Those are the three things that make integrals improper. One is if you have an infinity on top or a minus infinity on bottom. Those are improper. In this case, one of your bounds makes the original function discontinuous. So in this case, this bound of 0 makes this function discontinuous. I can't plug 0 into that function. And the third possibility, the one that's easy to forget and the one that's really easy to miss, is when you have something like this, where you have a discontinuity in between your bounds. In this case, I have a discontinuity at 0. So that would be considered an improper integral. All right, so what you're going to do on these, this is probably a bad example because I think the answer for all three of these is going to be doesn't exist, but that's okay. What you do, if you have an infinity on top like this, you're going to take the limit as b goes to infinity of the integral from 1 to b of 1 over x dx. So you can see why L'Hopital's rule was taught right before here, because we're going to end up dealing with a lot of limits. Limit as b goes to infinity, integral from 1 to b.
So that only works when there's infinity in the integral.
Correct. So if there's an infinity here, you're going to do limit as b goes to infinity.
If it's in the bottom,
If it's in the bottom, then we would call it a. That's right. If we had a negative infinity down here, then we would say the limit as a goes to negative infinity. We always use a for the bottom number and b for the top number. Why? I don't know. That's the way they're picked. We always go a and b. All right. So now, if this limit happens to exist, then that'll be our answer. But in many cases, you're going to find the limit doesn't exist. In which case, your answer might be does not exist, or it might be infinity. You might say your answer is infinity. And I think this one's a good example where this answer is infinity. Why do I think this answer is going to be infinity? What do integrals tell us again?
area.
Integrals tell us area. So if I draw the graph of 1 over x, and I go from 1 to infinity,
You're always going to have an area.
my area is going to keep getting bigger and right. My area is going to keep getting bigger and bigger and bigger, isn't it? So I think our answer here is going to be infinity. Well, let's just look. This would be the limit as b goes to infinity of ln x evaluated at 1 and b. That's the limit as b goes to infinity of ln b minus ln of 1. ln of 1 is 0. But what happens when b goes to infinity? Ln of b goes to... It goes to infinity. Infinity minus 0 is infinity. So we would say our answer there is infinity.
Now, eventually, can you just kind of look at these integrals and just be like, well, that's how it's going to be? Because you're going to look at that because you think about it, it's the natural log. And if you have 1 as the lower bound, and the 0 and the positive against the right, depending on those you have. I'm not saying all problems.
Certainly not all of them. And we can find some here in a minute where our answers won't be infinity. In fact, let's see if I can find one. See if I can pick a good one. Oh, I'm not going to look in the back of the book. I'm just going to look at them and find one that works.
So you think exactly what I just said?
How about the limit? How about the integral? From 1 to infinity of 1 over p. Why did I use p? I don't know.
P to the third?
1 over p cubed dp. All right, again, we would write this as the limit as b goes to infinity. The integral from 1 to b of 1 over p cubed dp. That's the limit as b goes to infinity. What's the antiderivative of 1 over p cubed? Think of that as p to the negative 3.
So 1 over negative 1 negative 4 p to what?
About
P to the negative 2.
p to the negative 2 over
Oh, plus
negative 2. You got to add 1 to your power, correct? You guys were subtracting 1. You guys were giving me derivatives.
yes.
Evaluated at 1 and b. So that's going to be the limit as b goes to infinity of b to the negative 2 over negative 2 minus 1 over negative 2. So now what happens when b goes to infinity? When b goes to infinity, what happens to b to the negative 2 over negative 2? Gets close to 0. Why does it get close to 0? Think of b squared as b to the negative 2 is going on bottom. That's right, it's 1 over b squared. So when b gets really big, 1 over b squared gets really close to 0. So this is 0 minus negative 1/2. So there's an improper integral that converges. We would say that converges to the answer of 1/2. So what that means is, what's the graph of 1 over p cubed look like? I think it would look something like this. So if I start right here at 1 and I go to infinity, is my graph ever getting to my axis? Am I ever really hitting 0? No, but what's happening is eventually it's getting so close to 0 that I'm not really adding any significant amount of area. So my answer is simply 1/2. That would be the area under that curve. Questions on that?
For the last one, for the 1 to infinity,
Uh-huh.
or for 1 over x, isn't that like a similar looking function though? Where it's like,
It is a similar looking function. So I agree, that's interesting. That 1 over x has the same shape.
yeah. It's just asking for its own x1 axis.
So if I start at 1. But what happens is it doesn't get small as fast as that one gets small. And so this one, it gets small, but not so small that eventually you're not adding an insignificant amount.
And then the way you work it out, you don't get natural log.
Right, and I picked it so that I would not end up with a natural log.
It's just interesting because there's a big difference between 1/2 and infinity.
Yeah, there's a big difference between 1/2 and infinity, I agree. So just by slightly changing the function, you get very, very different answers.
Zero to 5 of 1 over x dx. Do you just set a to 0 because that's where it's improbable?
All right, so let's do that problem. So if I asked you to evaluate the integral from 0 to 5 of 1 over x dx, you would indicate that 0 is the problem area. So what you would do this time is you would take the limit as a goes to 0 from the right of the integral from a to 5 of 1 over x dx. How come you take the limit as a goes to 0 from the right? Why not just the limit as a goes to 0?
Because it's not
true,
But that's the value.
all of our numbers are between 0 and 5, right? So that's why I want A getting close to 0 but bigger than 0. Because our numbers are between 0 and 5. We're not using any negative numbers, are we? All right, so we integrate. This is the limit as A goes to 0 from the right of ln x, evaluated at 5 and A. That's the limit as A goes to 0 from the right of ln 5 minus ln A. So this one is 5, that one's okay. But when A gets close to 0, ln of A gets close to negative infinity. So it's ln of 5 plus infinity, which is infinity. So again, that one's not bounded. You get an infinite amount of area there.
But don't we have actually, why is it plus infinity? Because it goes negative.
Because we got a minus there.
Right.
And when A gets close to 0, ln of A itself gets close to negative infinity. So this piece alone is a negative infinity, but then I've got another negative sign. Okay, questions on that?
So I don't really see, I'm sure that these are going to much more different when back to manipulation when we do this out, but so far I don't really see any need to do any test rules or anything like that.
So far, I don't see any need to do any L'Hopital's rule or anything like that.
Because most of the things you just use standard logic, you take the integral, and then logically look at it and say this is approaching this is approaching this. Kind of like what we did with derivative. We had to use a logical approach to figure out the answer.
Okay. How about the integral from 1 to infinity of 1 minus x e to the negative x dx? Well, once again, we would have the limit as b goes to infinity of the integral from 1 to b of 1 minus x e to the negative x dx. Now is where the fun comes in. How do you find the antiderivative of 1 minus x e to the negative x?
I would distribute the e to the x. I would distribute e to the x first, and split it, then do parts of x times e.
But in either case, you have to do parts, right? So I think it might be easier to just leave it the way it is and just do the parts. So I'm going to let, what should I let u be? 1 minus x. And then dv is e to the negative x dx. Sure, we can do tabular method, because when we take the derivative of 1 minus x is going to be negative 1, and then the next derivative is going to be 0. Over here we integrate. The integral of e to the negative x is negative e to the negative x. We integrate again, we get e to the negative x. So plus, minus, plus. I'm going to end up with the limit as b goes to infinity of that one, which is going to be negative 1 minus x e to the negative x. And then this one, I'm going to have two minuses, so that's going to be a plus e to the negative x. I got to plug in my numbers. All right, so I plug in b. Skip down here. I'm going to have the limit as b goes to infinity of minus 1 minus b e to the negative b plus e to the negative b minus, and then I plug 1 in. But when I plug 1 in right here, this is nice because 1 minus 1 is 0. So all that's going to be 0. E to the negative 1. So now, how do I find the limit as b goes to infinity of 1 minus b times e to the negative b? Well, when b goes to infinity, 1 minus b goes to negative infinity, and e to the negative b goes to... It goes to 0, doesn't it? Because that's 1 over e to the b. So this is in the form infinity times 0. So what do you do when you're in the form infinity times 0? You move one of them. Correct. Which one's the easy one to move? Minus 1 minus b or e to the negative b? E to the negative b is the easy one to move, isn't it? You move it to the bottom and it just makes the power positive. So this is going to be the limit as b goes to infinity of minus 1 minus b over e to the b plus 1 over e to the b, I'll just put that one there, minus e to the negative 1. And here's where L'Hopital's rule comes into play. What's the limit as b goes to infinity of 1 minus b over e to the b? That's in the form infinity over infinity now. Take the derivative of the top, you get negative 1. You take the derivative of the bottom, you get e to the b. So negative 1 over e to the b when b goes to infinity is going to be 0. So this one's going to be 0. That one's going to be 0. You don't need to do L'Hopital's rule on that one, do you? So 0 plus 0, 0. So our final answer is minus e to the negative 1. So there's where L'Hopital's rule starts to come into play with these. L'Hopital's rule will come into play when the integrals are more challenging, when you have to do integration by parts or partial fractions or any of those other techniques that we did. Aaron?
Do you even have to plug anything in because you get negative 1 over e to b plus 1 over e to b?
When I simplify that?
Because you take the derivative of that.
That's right. So I get negative 1 over e to the b when I take the derivative.
Oh, yeah.
And then when b gets really, really big, I've just got negative 1 on top and fixed on top. B getting bigger and bigger. I got 1 over infinity form. That's 0.